Hello, everybody. Thank you very much that I can be here and give this presentation. So my name is Maximilian Klammer. Just call me Max, that's simpler. I'm leading the R&D department at ChromaSense, and I want to talk today about shortwave infrared cameras, LED illumination, and of course, the perfect match inspection solution, which always needs the camera, the lens, and the light, so everything together. So, okay. So, short introduction, what I will be talking about again, quickly about shortwave infrared, what it is, the imaging application materials. I think it's maybe the most interesting part. The most common technology used here, the indium gallium arsenide sensors. And of course, since ChromaSense, we are, let's say, 95% focused on line scan cameras. I will, of course, talk here about shortwave infrared line scan cameras as well, and also what you need to make it work. Finally, talk about accessories and light source, of course. So we also have now extended portfolio to the shortwave infrared LED light sources. Okay, shortwave infrared imaging, what is it actually? So most of the common cameras, if it's mono cameras, if it's near infrared or color cameras, all of them are based on silicon sensors. And I think it's a great match. So silicon is one of the predominant materials on our Earth, and it's well examined, and it's absorbing light in the visible range from 400 to 850 nanometers. So it's a perfect match to build sensors and also, of course, electronics out of it. But if you want to inspect, or if you want to sense light, which goes beyond the 850 and 900 nanometers, so going into that direction here, you need a different material because, yeah, silicon is a semiconductor. You need energy, photon energy higher than the 900 nanometer, otherwise it cannot be absorbed. So we need a smaller band gap below that, and we can go here with indium gallium arsenide sensors. So you can perfectly extend the sensitive range of your system using a silicon camera and indium gallium arsenide. So if you have a short look onto the complete electromagnetic spectrum, the visible range, we are about here above 1 micron, and the infrared range. And if we blow it up, we have here the near infrared, which can still be covered with silicon-based cameras. So yeah, from 750 to maybe 850, 900. And then we have the shortwave infrared, where we can go for the indium gallium arsenide. And if you extend further, then it's more like bolometers, microbolometers, and completely different technologies used here. Okay, so just a short recap. Silicon is getting transparent in the near infrared, and here indium gallium arsenide is a perfect choice because it has a smaller energy gap and it can absorb photons with less energy than those of the visible range. And yeah, and again, so since it's such a perfect match, most of the cameras today available in that range are using indium gallium arsenide. There are new technologies upcoming with energy conversion, non-linear effects used here, but I think that's still most important, the indium gallium arsenide. Of course, you need light. And again, if we have the V lambda curve of here you see the visible, the human perception of the spectrum, the silicon sensor, which covers it well, and then a different kind of near infrared LEDs and also shortwave infrared LEDs. So in the past, or in the last years, months, there have been several developments, and we have more and more high power LEDs in the shortwave infrared range. It's not so difficult actually for this material scientist to build LEDs, but it's very challenging to do high power, high efficient LEDs. So there was also, of course, a very important Nobel Prize for the high power blue LEDs, which finally made it possible that we have white LEDs everywhere in houses, buildings, cars, and machine vision as well, of course. But also here in the shortwave infrared, increasingly, we have more power. And yeah, so far, most of the machine vision applications still use halogen light sources. There are some drawbacks, but also, of course, some upsides. So it's broadband if you go with a halogen light source. But if you talk about durability, heat, energy consumption, LEDs are, of course, the better choice. And also LEDs we can use in flash operation. I will explain later what that means, because it can be interesting for many applications that you use different wavelengths to measure a certain kind of defect you want to use for sorting or inspection. Okay, applications. Let's have a look in here. I think it's maybe most important. Again, so this is our view, of course, with existing customers and experience on the market. I would be very happy for any discussion later on or also after that meeting, what kind of applications and challenges you see in your fields. But of course, recycling waste prevention in plastics is a big topic, because the plastic material can have different reflectance properties in the shortwave infrared. There are applications for cotton cleaning, cotton sorting, cotton inspection. I will also show some more details. Quality check of fruits, grain sorting, seed sorting is a huge thing. The fully automated sorting of it's tremendous. They really scan every single seed and check for quality, and little stones and contamination are blown out then based on the image data. If you talk about semiconductor manufacturing and renewable energies, of course we can use it that silicon is getting transparent in the shortwave infrared range, so we can use the shortwave infrared for inspection and transmittance. So we can then see defects in the material, like inner cracks, or you can see the printed electrodes, like in a shadow. If you have a backlight shortwave infrared, then you can see the printed screen printed electrodes on the solar cells. Different kind of substances, materials, of course, can have change in absorptions and reflectance in shortwave infrared. So those are also use cases. Of course, having a closer look into plastic sorting, I think it's obvious. We are producing plastic like hell, and we cannot just burn all of this. I think that's now clear to everybody. So we have to sort it and to recycle. And the very important condition is that you have to separate very carefully the different kind of materials that you're able to use it again and recycle it. And shortwave infrared imaging can be part of a sorting solution in this big sorting machines. So we have done an extended feasibility study on different kind of plastics. We have been using more wavelengths, but we applied machine learning approaches, and we choose those 3 wavelengths, which showed us the highest significance in separation of the different plastic materials. And here you can see some results where we do a pixel by pixel classification based on the 3 wavelengths for all these materials like PE, PET, PP, PS, wood. Wood is the background as a reference. And yeah, we see that we can really do a good job here just by a minor set of wavelengths. But of course, there are also different technologies needed to have a full separation later on in the sorting machine. But it's very promising what we see here. Another application is, for example, in the field of cotton. So if the cotton is brought in from the field, they put it in like big plastic bags. And these big plastic bags, they are these kind of woven plastic fibers, and you can have contamination from those. And it's very, very hard to see them because they are white. Cotton is white, the plastic is white. But we did scans on those with a hyperspectral camera, and we saw that there is a significant change of reflectance of the plastic in a certain wavelength. So we can use now maybe the maximum and the minimum, put on both positions selected LEDs, and then we do a difference image, and then we can emphasize really where is the plastic fibers here in the sample, or we can also using simple thresholding just make them even more visible. So this is also one study what we have done to understand use cases for shortwave infrared imaging. And all those are use cases where line scan imaging is, of course, very useful, because you have a continuous transportation of the material, and typically also at high speed and high resolution. Food inspection and sorting, very important. For example, here you can see example that if you have coffee beans and a stone in between and a visible, it looks really like same color. But if you go on the shortwave infrared, you can see a different signature. So here it's also very helpful to do a reliable cleaning or sorting of grains, beans, any kind of this dry agricultural products. Of course, also, let's say, quality inspection here, like fruits, where you could have like a bruise, like a dent or something. It's also very, very helpful. Again, if we talk about renewable energy or semiconductor inspection, if you have like from the backside, for example, visible image, if you go with a backlight in a shortwave infrared, you could see the structures. For example, like if there are already metal parts coated on, because metal, of course, is more or less to all wavelengths, or is to shortwave infrared wavelength reflectance, so not transparent, that it can structures be seen, or cracks, or similar things. So I want to have a brief look into SWIR line scanning cameras, since ChromaSense is focusing again 95% on line scan cameras and line scan solution, line scan light source. I will have a closer look here. So we have our allPIXA SWIR. It's available, it's an InGaAs sensor, as before discussed, sensitive for 950 to 1700 nanometer. We have like two sensor versions. One has a 25 micron pixel size, the other one is half the size, 12.5 micron, and corresponding, we have one version has 500 pixels, the other one is 1K. It's half an inch sensor size. We offer GigE and camera link, so dependent on the line rate or also your preferred interface for your integration, you can choose up to 40 kilohertz line rate, and with a C-mount interface, where you have quite some lenses on the market, where we also, of course, like to help to recommend suitable lenses. It's a very compact camera. It's like 62 by 62 millimeters. So it should find its place in nearly any machine. Quickly talking about features, of course, GenICam compliant. We have a lot of grabbers tested with the cameras. We have the standard image signal pre-correction internal, like dark signal and PRNU correction. We have a binning functionality integrated, also encoder features, where you can rescale the incoming trigger pulses to the desired transport resolution. And of course, the line-wise acquisition can be used for flashing, that you can scan the one object with different wavelength in one shot, let's say. And of course, we also offer the light, as discussed before. The LED SWIR, you save a lot of energy. It's in terms of life cycle, it can operate much more time, much longer, the complete life cycle of such a module. You can have narrow band if you need, like what I showed before, like a difference in absorption. You can benefit from a small illumination spectrum or even more. We can flash them, and yeah, we can in a modular system, we can different kind of LEDs can be also put in one module. Yeah, halogen light sources, of course, can be used if a very broadband light is needed, but there are also, of course, some drawbacks on that side. The features we can offer here, it's a highly effective design using huge mirrors and LEDs, of course. Less maintenance and also reduced service cost. It's very easy to replace. And yeah, it's a high power module, really using the latest LEDs and technologies and high effective reflectors. So there are very little losses here, because yeah, as you know, with camera lenses, you cannot use normal glasses. You need specific lenses also for the shortwave infrared. But if you use a reflectance like a metal coated foil, it can work in nearly all wavelengths, let's say from visible to infrared. So at the moment, what we can offer is like 4 different wavelengths in a single module, or also we could combine them in one module if you like. So if we combine them like 3 wavelengths in one module, the minimum size is 340 millimeters, and then of course you can double or triple the size. With a single wavelength, the module length, the smallest is 170. And yeah, all of them can, it's like a toolbox. We can put them together also with different cooling options. And yeah, so it's like different building blocks we can put together here. Okay, short conclusion. Yeah, there are a lot of interesting applications. Also, I think applications which will be very important for the future, also for all of us. And we can offer here combinations and recommendations of camera plus lens plus light source. We can put all these different components together, and we also could build fully customized modules. We do this customization for machine builders. Yeah, and this can help to even increase performance and also reduce service cost. Okay, so now you have all the contacts you need. Maybe if you're interested in the future to talk with us about applications, requirements, we'll be really happy to learn more. So myself, Maximilian, I'm head of R&D at ChromaSense. We have Klaus Karcher, my colleague. He's project manager for SWIR cameras. We have Martin Merkler, who's our professional for light sources, also project manager for shortwave infrared light sources. And of course, Pascal, our area sales manager, EMEA. So that's it. Thank you.
So, hello, Max. We have already a lot of questions.
Oh.
So I hope you're prepared for the end, for everything.
Maybe I need a telephone joker. I don't know.
maybe not. Can you really ensure 95% sorting purity in plastic sorting using only 3 wavelengths? And what about PVC?
Yeah, what I said is we did a basic feasibility study. We did not build a complete sorting machine to analyze really the capability of that approach. And yeah, we did so it was we generated basic understanding on our side because we want to really know what we can do with that system. But we need a partner still to build the machine. So if there's somebody interested, we could do this together.
Get in contact with Max. And there's a question, does the SWIR line scan camera or maybe lighting is suitable for medical or pharmaceutical inspection fields?
Yeah, definitely yes. It really depends here on the kind of materials and the reflecting properties. Yeah, I think, of course, in medical there are many applications you can solve with mono cameras. There are many applications you can solve with color cameras, and definitely yes, also for shortwave infrared. But honestly, I'm not an expert in that field. I would be interested to understand what could be the application.
What surfaces reflect the infrared light properly? Would aluminium coating be okay?
So infrared, so more or less all metal surfaces reflect infrared. So if you go from metallic materials or metallic surfaces, and if they are thick enough, they will reflect all wavelengths from the visible till the deep infrared. Metal is just getting transparent in the UV and deep UV. It's getting more challenging.
And what is the importance of active cooling of the SWIR sensor?
We do not actively cool the camera. Of course, it always helps in any photoelectric device to reduce the operating temperature, but it's not a bolometer. If you have a bolometer array camera, of course, cooling is very important because the sensor sensitivity depends very much on the sensor temperature. But since we are still, it's the same effect we are using here, like with in silicon, a photon is absorbed and excites an electron hole pair across the band gap. So this process is not too much temperature dependent. The only thing which is temperature dependent is the dark noise. But dark noise temperature dependence is only important if you have long integration times. So since our line scan cameras are typically running at really short integration time, also dark noise level is not a big issue. Again, cooling is always helpful, but it's not a game changer here.
A lot of questions. I think we take one and we make the other one after the last presentation.
Sure.
Just one last question. Could we use the SWIR light and camera to see through the opaque containers, for example, HDPE bottles?
Ooh. So what I can say here, if you have a application in mind, we are offering to do initial feasibility tests in our house. So if you send us samples, or you're always invited to visit us, bring your samples. And after contacting our sales, we can do some tests in our labs and understand with which wavelength, which camera, can we see it in transparent. So we do a lot of interesting testing, even with living worms we had recently to scan them. So we can help here, but I cannot answer directly if it will work or not. We have to test it.
Okay, so Max, if you can close your presentation, we will go on with our next presentation. All the questions we have now will be answered at the end. Max will be there. For which use case or application does it make sense to use a SWIR line scan camera? And when makes it sense to use a SWIR area camera?
Generally, line scan cameras make sense when you have any kind of moving process. And typically also if you have really desire for also for color and mono cameras, if you need really, really high resolution of an object. Because yeah, of course, the INGAS is 1K. So here maybe the continuous transportation is more relevant. But if you also think about color cameras, you can go up to 16K, and in the other axis it's endless. So also in that sense, you can use you can do a 1K by whatever number of pixels scan. So yeah, the continuous process and the high resolution, that's normally the point where we would recommend also that really makes sense. There's one other point, it's for light sources. If you want to have a very homogeneous illumination on a big area, it's much more challenging than doing it on a line, because it's, let's say it's a one-dimensional problem. If you do it on an area, it's, for example, if you want to have a strict dark field configuration, that's very challenging with a matrix or with an area camera.
There's also a question, I think, about your cotton application at the beginning, Max. INGAS-based sensors are limited to 1,700 nanometers. At the cotton spectrum indicated, more accuracy of material identification would be possible by spectral information up to 2,300 nanometers. What is the development of sensors showing for such issues?
There's one version of the sensor available which has a little bit extended sensitivity, but it does not go up to 2,500. Yeah, and that's also the reason why we focus then on the peak on the 1,500 nanometer, not going to the strong peak on the 2,300, because yeah, the camera is not sensitive here. It's mainly limited by the material properties of indium gallium arsenide, and of course they can tweak it a little bit with dotting and stuff like this. But I do not think that it will drastically enhance in that direction. But maybe yes, there are also on silicon based sensors, there are a lot of versions available which have UV enhancement or have near infrared enhancement. But let's say if you go there, there's a point of, you have the band gap of the material, and then the absorption goes down to more or less zero. So then maybe we would really need a different kind of material to extend on the lower wavelength range.
And there's a question about SWIR illumination. How to select the right SWIR LED wavelengths for an inspection or sorting task?
Yes, again, what I have shown, so we had a institute external partner who did hyperspectral scans for us. Of course, it's always helpful if you have then the full spectrum and understand, and you can select really then where is the feature maybe to go for. So what we have also done, we just tested with the different wavelengths and just using image data and see where we have the highest contrast. So finally, whether we can do just, let's say, brute force testing, or we have to do extended measurements to understand which is the right choice.
So I would like to say thanks to my speakers, thanks to my audience. I hope you learned a lot of things about SWIR. I hope to see you at another webinar, maybe next week. And stay healthy. Hope to see you soon, maybe on a fair like latest on Vision.